Welcome to solverfy.
6.69. So we're told about some science fiction story that imagines an artificial planet that's made out of this sort of band encircling a star. The people live on the inside surface of it, and it's always noon, which is maybe a bit of a problem. And we want to imagine that this is the star is the same as our own sun, and that the distance from the band to the star is the same as the Earth-Sun distance, so 1 astronomical unit, and that the ring is rotating quickly enough that it produces an apparent gravity of g that's the same as on Earth, and we want to figure out what its period of revolution is in Earth days. So saying that we want an apparent gravity equal to that of Earth, on the surface of Earth, is the same as saying that the normal force experienced by someone on the inside of this has to be the same as g. And this will be the force from gravity. They're both pointing towards our star here. And then, of course, these have to add up to be equal to the centripetal acceleration, which is going to be mv squared over r. So writing down, that, we have the force of gravity plus the normal force has to be m times v squared over r. And so we know something moving around in a circle at constant speed, its speed has to be the distance that it travels, the circumference of the circle, divided by the amount of time it takes to travel that distance. We want f sub n to be equal to m times the g of Earth. And the force from the star is going to be g times the mass of the object times the mass of the star divided by r squared. So you just put these in and solve for the period. We have m times 4 pi squared. We'll have an r squared over r, so an r over t squared. Is equal to mg plus g mm sub s over r squared. So the mass of our hypothetical person or whatever on the surface, inside surface of this ribbon, band, whatever, doesn't matter, which is good. It would sort of be an indication that we've done something wrong if these didn't cancel out. So then the period is going to be the square root of 4 pi squared r over g times the mass of this star divided by r squared plus our 9.8 meters per second squared that we want the apparent gravity to be. And so then this works out to be 8.99 days. And if you go and work out what this is, because the Earth-Sun distance is so large, even though the mass of the Sun is also large, but the distance is large, and then g is very small. So it turns out you could actually ignore this in the calculation without really changing this a whole lot. That's sort of an interesting thing. You could just have this disk out spinning, in space, nowhere near anything else, and it would still need about a 9-day rotational period to produce an apparent gravity the same as the Earth's surface.